Okay, so our next speaker is Motonobu Kanagawa from Eurocom in France, and he's going to talk about positivity of the BQ weights. Please go ahead.
Thanks, Tony, for the introduction, and also for thanks to Tony and John for organizing the workshop. Sorry, my PC. So anyway, so the talk is about on the positivity of Bayesian quadrature weights. You can see my cursor, right?
Yes, we can see it.
Okay. And basically, the talk is, you can find the contents of the talk in this paper of the essential, similar title. And so this is joint work with Tony and Simon from Finland. Okay. And so this is the outline. So already, all the speakers have introduced the framework of Bayesian quadrature, but let me do it again to fix notation. So as you know, so Bayesian quadrature is a probabilistic numerical approach to integration or sampling. And for integrand, which is a function from here, we consider the domain to be Euclidean space. And also for probability measure nu, what we want to do is to compute the integral for which we do not know the analytic solution. Okay, so what we do what we do in Bayesian quadrature is that we first place a Gaussian process prior on the integrand. Okay, and here case a covariance kernel that you specify by yourself. Okay, then you somehow collect the function values. Okay, evaluated at the design points, and these design points are also, by definition that you design. Okay, then being a Bayesian approach, then you compute the posterior distribution of the integral. Okay, this is a probability distribution conditioned on these function values, which we regard as observed data. Okay, so because we use Gaussian process the prior for the integrand, so this posterior distribution is given also as a Gaussian distribution. Okay, and here I use this notation dn to mean these data or function values along with the data design points. And here, so this term is the posterior mean of the integral. And this second one here is the posterior variance. Okay, both of them can be obtained in a closed form. And let me just look at here the expression of the posterior mean. And this is given as a weighted sum of the function values in this way. So here f of xi, these are function values that you have collected. Okay. So and the t, so here these weights are given by matrix computation in this way. Okay. This is the weight vector that contains the weights. Okay. And so here the kx is the kernel matrix and by n matrix, and here k nu x is the vector that contains the evaluation of this integral, which is assumed which we assume to be analytically available. But if you use a kind of Stein kernel, then this is really may not be the problem. Okay. Anyway, if you case Gauss and nu is Gauss, then you can obtain this this expression analytically. Okay. And again, so this dn here is the observed data, and the case this kernel is the covariance kernel of the prior. So what what I'd like to point out here is that this expression is really commonly used form, and this is the same as Monte Carlo or importance sampling. And if nu can be written as this way, p of x with this dx derivative measure, so p of x is the probability density function, then importance sampling estimator is given in this form, that you want to approximate this integral in this form. Okay? And just using another density here, you can rewrite this one in this form, okay, in terms of the ratio of the two densities. And this can be approximated in this way. And where xi, so being a Monte Carlo, you generate from this proposal density in IID manner. And here the weights are given as the ratio. Here you can see here the ratio evaluated. Ratio of the two densities is evaluated at the design points, and these are called the importance weights. Okay. So by definition, it should be non-negative. Okay. So the question in this talk is that the weights of the Bayesian curvature, whether are they positive or not. So actually, so in the Kenshiro's talk, so we saw that this is generally no. Depending on the construction of the design points, some weights may be negative. Okay? So, and then the question might be rephrased in this way, that under what conditions do the Bayesian curvature weights become positive? So this is the main question in this talk. And why does this question, or why does the positivity matter? So conceptually, so if we know, if we can guarantee that weights are positive or non-negative, then we can interpret the weight, each weight, to represent the importance of the corresponding design point in approximating the measure that with which you want to integrate. Okay. And practically, this is a nice thing that basically you can show theoretically that if your weights are positive, then this leads to the robustness of the Bayesian curvature rule. By robustness, I mean that robustness to the misspecification of your GP prior, that maybe your GP prior might be smoother than the true integrand. If you lack knowledge about the integrand, this kind of misspecification can happen. Like if the integrand is defined by a simulator or black box model, then you may not have enough knowledge about the integrand. And so there are a few studies that relate the absolute sum of the weights to the robustness of the Bayesian curvature rule. And so in summary, so if this absolute sum is bounded, so if you increase the number of design points n, but still this one is bounded, then you can show that your GP and your Bayesian curvature rule can still give you a correct answer, a correct or good answer. Okay, and so in this paper by Tony and me and Shimo, so we also mentioned, summarize that it's really easy to show this, but if under very mild conditions, the positivity of weights imply this one. So this means that by using, so this means this, okay? So main result. So I would not really claim that this result is really new. Actually, this result has been known for decades, that since 1970s, but so to motivate discussions among us. So so I'd like to introduce this one. Okay, and because the theory is really technical, so we only focus on the case of invariant case. So let A and B are constants. So there should be squared here, but first we consider a kernel which is infinitely smooth, infinitely differentiable, and which is also assumed to be totally positive order 2. So definition is a bit complicated, so I omit here. But for instance, the popular Gaussian kernel is an example of this totally positive kernel, and also Hardy kernel is example. Okay, and so it is known that so if your kernel can be written in this way, then this is totally positive. That here AM, so this is an infinite sum, and AM is positive constant. AM are positive constants, and V of n x is positive increasing function. Okay. So maybe you could define V of x as, you know, maybe kind of polynomial. Okay, and you could interpret this as kind of Taylor expansion. And we also need an assumption of the design points. And so by xn, so I mean the set of design points, n points, okay? And this is a vector. And we assume that xn here is locally optimal in the sense that this function vzn, so we consider the partial derivative of this function and then insert these design points here, and we assume that this is 0. Okay, so the derivative vanishes, and this Zn here is just a variable vector, and here Vzn is the Bayesian quadrature posterior variance given these points zi, variables zi. Okay. And this is given by in this form. That the first term is the integral with respect to the kernel, and the second term is given by the kernel matrix, and also this vector which appeared in a previous slide. Okay, and so Luke in the morning session mentioned that this is actually MMD worst case error, or Tony also mentioned this one. So the distance, RHS distance between the kernel mean embedding of nu and that of the empirical measure. Okay. So and the result here is that so in this sense, so we assume that design points are locally optimal in the sense that this gives vanishing gradients. So maybe we could also say this as the kind of stationary point. Okay. So, under these two assumptions, okay. So let's recall that these are this is the formula for the weights of Bayesian quadrature, and then you can show that under these conditions the weights are positive. Okay. And you can find the proof for this in this paper. So this is our paper. So I think, yeah, maybe because I'm one of the authors, so I think this proof is the easiest to understand. So I would recommend this paper. But you know, essentially the same results have been known. For a long time in this not so popular paper, and also this thesis by Otta Shagen. So. And what is why is this result interesting? So that's why, and that's because that so first we can we have this implication that let's say if some of the weights of your Bayesian quadrature are negative, then this means that your points are not even locally optimal. Okay. So this means that you can use actually the weights to know the quality of the design points. That's one thing. And then, given that some of the weights are negative, then you can still optimize the design points by gradient-based optimization. What you need to try is to find points where the gradient vanish. Okay. Also another implication which is related to this one is that gradient-based optimization would be a promising approach for constructing the design points, because that from the previous slide, so we know that in that special case, at least theoretically, that if you try to find points on which gradients vanish, then so you will get positive weights, okay? And then the positivity of the weights leads to the robustness of Bayesian quadrature. So I think this is a nice point, okay? So, and we have numerical illustrations. And so here we consider the case of two-dimensional domain with a Gaussian kernel and Gaussian measure. Okay, and so we optimize the design points so that the posterior variance is minimized. Okay, and so I'd like to let you know. Point out that so this case is not covered in the theory because first this is two-dimensional, and also the measure here, the support is not compact. So anyway, so this numbers are the weights actually. Okay, so and this Gaussian measure has the mean 0. So you can see that so this points are nicely placed. And the center here has the largest weight. This is kind of reasonable. And the sum of the weights are 0.91, which is close to 1. There is a reason that you can expect the sum of the weights will be close to 1, because this is, you can consider that this is estimate of the constant 1, actually. That your integrand is constant function 1, okay? And so, and this is the case of, n being 11. So we have similar result here. And so as n increases, you can see that the sum of the weights is getting close to 1 and the same. Okay. So, yes. So you can observe that basically that these are really beautifully, I don't know, this is really subjective, but points are spread. And also that the distance between the two design points is not, not small. So this means that the separation radius that you mentioned is large. Okay, this is nice thing. So this is the future objections and questions. This is the last slide. So far the theory is only limited to the one-dimensional case. So and in practice we are not really interested in one-dimensional case. So and the question is how can we extend the theory to the multi-dimensional cases? And also the kernel, which has been considered is infinitely smooth. So then the natural question would be, what would happen if the kernel has only finite smoothness like Motonobu or Endrand? But in this case, optimal. There are also, in the literature, so a lot of things have been known about optimal quadrature rules. So, and this is references, but yeah, so that's it. Thank you.
Thank you for the talk, Moto. So now's the time for questions if someone has any.